You've probably heard it a million times. People who do X are more likely to do Y. But does that actually mean X causes Y? Well, that's one of the toughest questions in all of science. So today, we're going to unpack the really clever methods researchers use to move beyond those simple links and get to the real answer. Why? Here's the game plan. We're going to start with the core puzzle of causation itself. Then we'll look at how nature gives us its own perfect experiment with twins. After that, we'll tackle the tricky problem of time. And finally, we'll see how all these incredible tools come together in the search for why. All right, let's kick things off with the single most important rule in all of science. And honestly, the biggest headache for researchers, getting your head around the huge difference between correlation and causation. To make this super clear, let's grab a real-world example from a major national study. There's this common idea that being involved in religion helps keep teenagers on the straight and narrow. But is it really that simple? And sure enough, when you look at the data from thousands of people, you see a link. On average, teens who are more religious tend to be less delinquent. But, and this is a big but, finding a connection like this is just step one. It doesn't prove a thing about cause and effect. And this slide gets right to the heart of the problem. See, a correlation just means two things are moving together. Causation, though, that's a much bigger claim. It's totally possible that some third thing, what scientists call a confounding variable, like parenting style or even genetics, is the real reason for both the religiosity and the lower delinquency. So, how do we solve this puzzle? Let's move on to the first incredible tool in the researcher's toolkit, one that uses a pretty amazing natural phenomenon to try and untangle this mess. This really is the million-dollar question, isn't it? I mean, you can't ethically assign people to be religious in an experiment. So how on earth do you control for all those complicated background factors, genes, home life, you name it, that make every family different? And this is where the logic gets really smart. Researchers use identical twins because they're basically nature's perfect control group. Think about it. They share 100% of their genes and grew up in the exact same family environment. So now you can ask a much, much sharper question. If one identical twin is a little more religious than the other, is that twin also less delinquent? You're essentially holding the entire family background perfectly still. So when the researchers actually did this, when they ran this analysis on the national data, what did they find? A big, fat zero. Nothing. Exactly. The moment you control for that shared family background, the link completely vanishes. Poof. A more religious twin was no less delinquent than their identical co-twin. This is some seriously powerful evidence that the original connection probably wasn't causal at all, but was instead driven by all those other factors the family had in common.
You know, this reminds me of a fantastic quote from the legendary statistician John Tukey. He basically said that simple correlations can be flaky and misleading, but if you dig deeper for the real underlying structure, that's where you find the stuff that's actually constant and true about the world.
Okay, so the twin method is amazing for taking a snapshot in time, but that's just it. It's a snapshot. What about a totally different kind of problem? What if you want to understand how people change over time? I mean, across their entire lives? Well, this is a classic trade-off researchers face. On one hand, you could do a longitudinal study, following the same people for decades. It's the gold standard for sure, but it's incredibly slow and costs a fortune. On the other hand, you could do a cross-sectional study. You just compare today's 20-year-olds with today's 70-year-olds. It's way faster, but you never know if the differences you see are because of age or just because they grew up in totally different generations. So what's a researcher to do? Well, it turns out they've come up with some brilliant hybrid designs that let them have the best of both worlds. And here's the big idea. It's called a cross-sequential design. Instead of following one group of kids for 50 years, you follow, say, a group of 5-year-olds, 10-year-olds, and 15-year-olds for just a few years. Then you can kind of stitch their data together where they overlap. It lets you build a picture of development over a huge lifespan in a fraction of the time. It's genius, really. And it's not just one design. It's a whole family of them, like a set of specialized lenses. A cohort sequential design can tell you if teenagers today are developing the same way they did 20 years ago. A time sequential design can check if the gap between a 20-year-old and a 40-year-old is getting bigger or smaller over historical time. Each one is custom-built to answer a very specific kind of question about how we change. Okay, so we've gone from snapshots to decades. But what if we want to zoom in, like way in? How do we watch change as it's literally happening, moment by moment, like watching a new idea being born right in front of our eyes?
I mean, that's the real challenge, isn't it? How do you capture the process of learning itself, not just the before and after shot? How do you get that slow motion replay of the discovery?
Well, the answer is this amazing technique called the microgenetic method. You can think of it like a high-speed camera for the mind. Researchers find a kid who is right on the cusp of a breakthrough, maybe learning a new math concept. Then they just watch intensely. They collect a ton of data, trial after trial, to map the exact strategies, the mistakes, and that amazing aha moment of insight. So, we've looked at twin studies, hybrid designs, microgenetic methods, a whole bunch of different tools. Let's pull the camera all the way back out now and put it all together. What's the ultimate point of all these careful, complex methods? And this is so important. The real goal here isn't just to play the old nature versus nurture game. It's about being a good scientific detective. It's about using these powerful designs to really, truly test our theories about why things are connected. It means being a careful, skeptical scientist who knows that behind every simple correlation, there's usually a much more fascinating story. Look, at the end of the day, none of these methods are some kind of magic wand that just proves causation. They are tools for asking better, more precise questions. As the researchers in our source material put it so well, this is really just social science conducted a little more carefully, analyzed with a little more realism. In the end, it really all comes down to having the right tool for the job. Sometimes you need a wide-angle lens, like a twin study, to control for that big picture family background. And other times, you need a microscope, like the microgenetic method, to see all the tiny details of change. Together, they help us build a much more complete and much more accurate picture of why we are the way we are. So, we'll leave you with this final thought. Now that you've had a peek inside the researcher's toolkit, think about some piece of common wisdom you always hear about people. What's an assumption about what causes what that you would just love to put to the test? What's the big why that you're most curious to solve?